Hi everyone, greeting to all of you. Alright, untuk dalam video ini, okay, in this video we are going to learn about calorimeter. In chapter 2, thermochemistry, calorimeter is the second subtopic that you have to learn. However, as I told you before, I go to the third first and then the fourth, and I'm going to teach calorimeter as the last one. Okay, so in this chapter as well, we use this we in our experiment 2, we apply this subtopic in the experiment. Okay, calorimeter. So I guess calorimeter is something that you haven't learned in SPM before. So without wasting any time, let's proceed. Okay, in this topic calorimeter, we have 3 learning outcomes as you can see here. So what is the thing that you have to know? Okay, let's see. Okay, A, we have to define heat capacity and specific heat capacity. Okay, and then so ini we have to define lah. Okay, we have to define it. And then B, calculate the heat change in a constant volume calorimeter. C, calculate the heat change in a constant pressure calorimeter, which means you are going to be introduced with 2 types of calorimeter. The first one is the constant volume calorimeter, and the second one is the constant pressure calorimeter. So let's take a look at the first learning outcome, which is what is heat capacity and what is specific heat capacity. Before we going further to learn more about the calorimeter, so let's take a look at this photo. Okay, so we always we have get used to this one, right? Kita dah biasa tengok benda ni, and then usually for those who are on diet, katakannya lah kan, they're on diet, they will always use these nutrition facts to look at this area. Okay, which is the calorie intake. Okay, whenever you when you consume one packet of crackers, you are going to see how many calories, or satu mangkuk nasi tu berapa calories. So we always think about the calories whenever we want to control our food intake. Okay, when we want to lose our weight. And the question is, maybe you never think about it, but how do they know that like one bowl of rice is equivalent to 300 kilojoule, or maybe like this one, as you can see here, it says that per serving it will provide 220 joules or calories. Whenever you eat one serving is 43 grams. So whenever you eat 43 grams of this toast ghee, we are going to get 220 calories. So how do they know this? Have you ever think about it? Okay, so actually in food tech industry, they apply this calorimeter concept. Okay, they apply this calorimeter concept to provide these nutrition facts. Okay, dia bukan saja bagi, but actually they provide the what they call this, they do the study, okay, from the concept of calorimeter that you are going to learn after this. So let's proceed with this topic. Okay, so let's take a look first. In the laboratory, usually the scientists, they will use calorimetry. So calorimetry, as you can see here, it is a method used in the laboratory to measure the heat change of a reaction. And for them, okay, for the scientists or the food tech people, when they want to know how much calorie for each portion of the food, they will use calorimeter in this in this study. Okay, so as I told you before, there are 2 types of calorimeter that you're going to learn. Okay, the first one is the simple calorimeter, or also known as constant pressure calorimeter, and it is very simple. As you can see here, it is a very simple calorimeter. It is consists of a styrofoam yang cawan cup tu. Okay, and then this is the lid, okay, to cover the, what we call this, to cover the styrofoam, we have stirrer, and we also have thermometer. If you already watched the video for experiment 2, you can see how you can see this simple calorimeter. You also can set up it, no problem. Okay, so for simple calorimeter, the process is opposed to atmosphere. Okay, and then used to measure heat flow in a solution. So we are going to use this for a solution. Okay, for a solution. And then as you can see here, it is suitable for measuring enthalpy change that take place in an aqueous solution. For example, neutralization. Okay, because neutralization, we are going to add hydrochloric acid and sodium hydroxide. So when we mix them together, they have their own reaction, and then you can usually neutralization, it is a heat release reaction, so it will release heat, and you can see the increase in this thermometer, and then you can measure, and then you know how much temperature increase, and then you can do your calculation. But how about bomb calorimeter? Okay, this is what we call bomb calorimeter. Okay, we are not going to make bomb here, and it is also known as a constant volume calorimeter. So this is the setup. Okay, it is quite complicated. If you ask me, I never seen it before. Even in university, I only seen this every year except this year. Your year we don't see it. Okay, so this is the bomb calorimeter. So usually this is what the scientists or the food tech will use. Okay. Now, as you can see here, the process occur in a sealed container. So this is the container. Sorry, no, this is just not the box. This is the container. Okay, this is the container, and then used to measure heat flow for gases, and it is used more in enthalpy of combustion. Okay, so I will explain to you how bomb calorimeter work in another video so that you can understand more about this. But for now on, I would like to introduce to you what is heat capacity and what is specific heat capacity. Okay, as you can see here, we have heat capacity and specific heat capacity. So what is the definition of heat capacity? Okay, heat capacity is actually referring to the amount of heat required to raise the temperature of a sample substance by 1 degree Celsius. So usually students will get confused with heat and temperature. Okay, heat is the energy, temperature is the reading, right? So for heat capacity, okay, you want to find out how many heat required to raise the temperature of one sample, okay, of a sample of a substance by 1 degree Celsius. Okay, and then for specific heat capacity, but before that, heat capacity, the symbol is big C, okay, large C. Okay, and then how about specific heat capacity? Okay, we call it specific because it is very specific, because as you can see the definition here, the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay, so this is the unit for heat capacity, and this is the unit for specific heat capacity. Now, let's take a look at this. The specific heat capacity of water is 4.1 joule per gram per Celsius. So what is the meaning of this? Okay, means 4.18 joule of energy is required to increase the temperature of 1 gram of water by 1 degree Celsius. Okay, so maksudnya dalam 1 gram water, okay, dalam 1 gram air, untuk kita naikkan 1 degree Celsius, kita perlukan 4.18 joule tenaga haba. Itu maknanya. Alright. So more the specific heat, more the energy required for heating the substance. So material of high specific heat can be used as insulator. So I will show you another example for this. Fun fact about heat capacity. In our daily life, we always use the pot and the kettle and what else? The pan, the kuali, right? So all these things are made from materials with a low heat capacity. Low heat capacity means it only requires less energy to raise the temperature to 1 degree Celsius. So less energy means the temperature will increase faster. However, at the handle area, it is always made up from materials of high heat capacity, right? So that means it requires more energy to increase the temperature to 1 degree Celsius. Let's take a look at this pot. We usually use this pot to cook Maggi, right? Okay, now imagine every time we cook it, we are going to heat the whole pot at the same time, which means the body and the handle. However, we don't feel, we can still hold the handle. We don't feel it hot compared to the body of the pot. And why this happen? Okay, this is because the body part of the pot is made from a low heat capacity material, which means it requires less heat to increase the temperature. So less heat only require less heat and then the temperature increase, which means it easy to feel hot compared to the handle side where it is made from a high heat capacity materials which require more energy to increase the temperature. That is why the handle area will feel less hot compared to the body of the pot. Now in this video, let's talk more about calorimeter. In calorimeter, the basic principles that is applied is heat released by the reaction will be equals to the heat absorbed by the surrounding. As we know, whatever heat that released by a reaction, of course, we cannot we cannot identify it, okay? Cannot identify it. For example, like if you burn something, okay? Kita burn something, kita bakar something, and then, of course, kita tak akan tahu berapa banyak heat yang dihasilkan. Okay, so that is what we call heat release by reaction. However, walaupun kita tidak tahu berapa banyak heat itu terhasil, tetapi kita masih boleh mengira berapa banyak heat yang terhasil tadi dengan mengaplikasikan mengaplikasikan prinsip berikut, iaitu heat released by the reaction is equal to the heat absorbed by surrounding. But what is surrounding? Surrounding may refer to the calorimeter itself, or the water or the solution, or the third one is the water and the calorimeter, which means the calorimeter and the water will absorb the heat that is released by the reaction. So this is what we call surrounding. Let's take an example, the bomb calorimeter. This is the body of the calorimeter, or we can just call it as calorimeter. And this is the water. Now, we have one substance that we want to know how much heat in the reaction. For example, like maybe we have a carbon here. Okay, we have a carbon here. So what will happen? Okay, this is where the electrical condition started to ignite the fire. So maybe we have a switch here. Okay, for example, on the body of the calorimeter, we press the switch and the electrical will be supplied here, and it will ignite the fire and burn burn this carbon. Okay, so it burn, okay, the burn. And when the carbon is burned, heat is released. Okay, heat is released. Now, when the heat is released, okay, when the heat is released, this is what I said, that whenever heat released by any reaction, we don't know how much the heat released. We don't know. We cannot identify it. However, by applying the principle heat release equal to heat absorbed, so what will happen? All this heat release will be absorbed by water and by calorimeter. And what will happen? The temperature will increase. Okay, the temperature will increase. So we will take the reading of the temperature. Okay, we will take the reading of the temperature. Once we get the reading, then we will do the calculation. So how are we going to do the calculation? Okay, so for the first example, we are looking at the situation where the heat released by direction will be equal to the heat absorbed by calorimeter only. Calorimeter only. So there are two formulas that we are going to apply. Okay, let me introduce first. QRXN means heat released by the reaction. Okay, so heat released by reaction. This is your QRXN. Okay, RXN is actually stand for reaction. Q is stand for heat, which will equals to the heat absorbed by calorimeter. So for heat absorbed by calorimeter, we are going to apply two types of formula. Either we are going to apply this and this one. Okay, MC delta T and C delta T. So what are there? Okay, you are going to see some of the symbol. MS is equivalent to mass of solution. Okay, like here we have MC. MC is referring to the mass of calorimeter. Small c, which is the specific heat capacity of calorimeter. Okay, big C, heat capacity of calorimeter. And delta T is the temperature change. Okay. Okay, so let's take a look at the questions related with the situation that I show you just now. Okay, as you can see here, in an experiment, 0.1 gram of hydrogen gas and excess of oxygen gas were compressed and placed into a calorimeter with heat capacity of 9.08 exponent 4 joule per Celsius. The initial temperature of the calorimeter was 25 degrees Celsius, and finally it increased to 25.15 degrees Celsius. Calculate the amount of heat released in the reaction to form H2O expressed in kilojoule per mole. Now, let's take a look at this question. The data given to you is heat capacity. Okay, you are given heat capacity, and the heat capacity given to you is the heat capacity of the calorimeter. Okay, so heat capacity, as we know, it is a big C, so 9.08 exponent 4 joule per Celsius. And you also given the initial temperature of the calorimeter, which is initially it's 25 degrees Celsius, and finally it increased to 25.15 degrees Celsius, which means your delta T should be T final minus T initial. Okay, so I just get it, 0.15 degrees Celsius. Okay, and then you were asked to calculate the amount of heat release in the reaction to form H2O, okay, to form H2O expressed in kilojoule per mole, which means we are going to look for the heat release when we form 1 mole of H2O. So how do I know it is for 1 mole H2O? Okay, because in the end it says expressed in kilojoule per mole. Okay, this is very important for you to understand. Per mole. Now, as you can see here, the only data that we have is the heat capacity and delta T, and that's it. Okay, that's it. And calorimeter only, no water, no solution. So we are going to apply the one that I showed you just now. Let's see how are we going to solve the questions. Now, the first thing that you have to do is to write the equation. Okay, so we have hydrogen gas reacted with oxygen gas and to produce 1 mole of H2O. Make sure, don't forget to write the gas, the stat, and also balance the equation. So we have, this is the equations. Now, next thing is we need to find the number of mole for hydrogen gas. Now, since in these questions you are given the mass of the hydrogen gas, okay, you are given mass, so we are going to apply the formula mass over molar mass, so which is 0.1 gram over the molar mass of hydrogen gas, which is 2 gram per mole, and we are going to get 0.050 mole. Therefore, we know that in this reaction we have 0.05 moles for hydrogen gas, and for water, okay, in this experiment it is produced as 0.050 mole of water. So heat release in this reaction, which is when the 0.050 mole of H2O produced, is equivalent to this, the heat capacity of the calorimeter multiplied with the delta temperature, or the change of the temperature, which is this one, the heat capacity of the calorimeter and the change of the temperature. Calculate it, and we are going to get this one, which is 13,620 joule. Therefore, we can conclude that in producing 0.050 moles of H2O, heat release is equivalent to 13,620 joule. But if you remember, we are looking at the answer for the formation of H2O in 1 mole. So, by using the stoichiometry, we know that for 1 mole, for the production of 1 mole H2O, the heat release is equivalent to 272,400 joule. But we haven't done yet because the question is asking you to answer it in kilojoule per mole. So make another assumption. Heat release in the reaction to form H2O is 272.4 kilojoule per mole, or you can answer it as this, negative 272.4 kilojoule per mole. So maybe you might wonder, what is the difference between the first answer and the second answer? Now, the first answer, when you write heat release in the reaction to form H2O, you already mentioned the word heat release. So, in exam, the examiner will understand that you understand the reaction is about heat release. But if you don't do this statement, the heat release in the reaction to form, if you don't write this statement, there you have to add the negative sign. So the negative sign is the symbol of heat release. Can you understand, guys?
Now class, try this tutorial book Q6.
Now in the second situation, in whatever reaction happen and in whatever heat released by the reaction, it will be only absorbed by water or by the solution. Okay, which means we neglect the absorptions of heat by the calorimeter. We assume that the heat reaction only be absorbed by the water or by the solution. So if you happen to see a question like this, you have to apply this principle. Heat released by reaction will be equivalent to the heat absorbed by water or heat absorbed by solution. So usually we are going to apply this formula. Now, W is referring to water and S is referring to the solutions. So if you are applying or if your question is involving water, the mass should be mass water and the specific heat capacity should be the specific heat capacity for water. If the question says solution, then the mass should be solution. The specific heat capacity also must be solution. Do not mix the info of mass of water and maybe the specific heat capacity. You are using the solution. No, all right? So how are we going to apply this kind of questions? Let's take a look at the next slide. Now, this question is taken from the tutorial book. Let's see. When 200 milliliter of 1 molar sodium hydroxide was mixed with 150 ml of 1 molar hydrochloric acid in a styrofoam coffee cup calorimeter, the temperature rose from 25 degrees Celsius to 30 degrees Celsius. Calculate the heat of neutralization. Assume that the specific heat of solution is 4.1 joule per gram per Celsius and the density of solution is 1 gram per milliliter. So you can assume that we have a styrofoam cup and we add sodium hydroxide and we also add hydrochloric acid and they're going to mix together here. Okay, undergoes neutralization and they will produce heat. The reaction will produce heat. Okay, and of course, like I said, when the reaction release heat, the heat will be absorbed by the solution. Okay, of course, there will be a solution here. Now, given here, only the specific heat solution, which is 4.1 at per joule per gram per Celsius, and the change of the temperature, which is from 25 degrees Celsius to 30 degrees Celsius. We need to calculate the heat of neutralization. Heat of neutralization is referring to 1 mole of H2O produced. Okay. However, the change here, which is 25 degrees Celsius to 30 degrees Celsius, is when 200 ml of NaOH react with 100 ml of 1 molar hydrochloric acid. So, what we should do? The first thing that we have to do is to find the mole for H2O. Okay, now to find the mole of H2O. Okay, why we need to find the mole of H2O? Because the question is asking the heat of neutralization. And in order for us to find the mole of H2O, we have to find the number of mole for hydrochloric acid and NaOH first. So for this, we are going to apply the formula mv over thousands because we have volume and concentration. Okay, substitute the value and we are going to get 0.20 mole. The same thing is we have to calculate the number of mole for sodium hydroxide. The same formula. Substitute everything and we are going to get 0.15 mole. And as we know, the equation shows that everything, which means hydrochloric acid and sodium hydroxide, react in the ratio of 1 to 1. However, given the mole for you is 0.2 mole and 0.15 mole, you have to identify which of these is the limiting reactant. So of course the limiting reactant here, okay, the limiting reactant here is NaOH, okay, NaOH. And because the ratio is 1 to 1 and also the production of the H2O is also 1 to 1, we can conclude that the number of mole H2O produced in this reaction is 0.15 mole, which means in this reaction 0.15 mole of water is produced. Now that we know that the mole of water produced in this reaction is 0.15 mole, now let's take a look at other things. To calculate the heat release in this reaction, as you can see, we are given a styrofoam coffee cup with the specific heat capacity of the solution equivalent to 4.18. So we are given the specific heat solution only. We don't have any heat capacity or specific heat capacity for the styrofoam coffee cup, which is the calorimeter. Now, if we don't have the data of the calorimeter and we only have the data of the solution, assume that the heat released in this reaction will only be absorbed by the solution. So we apply mc delta T just like this. Now, we need to find the mass of solution. However, in this question, we don't even have any data about the mass of solution. Worry not, we have the volume of solution, which is 200 ml plus 150 ml. Now you might wonder why we have to add the volume of the sodium hydroxide and the hydrochloric acid. Because in this reaction, once they were added up, only the neutralization happened. So the heat release will be absorbed by, of course, the total of both volume. Now, the total of the volume of solution is 350 ml. But madam, this is volume of solution. This is not the mass. Hey, worry not, we are given the density of the solution. We are given here, okay, density of the solution. So from there we can get the mass of solution, which is 350 ml times or multiply with 1 gram per milliliter, and we are going to get 350 gram. So from this data, we substitute it into the formula. Now, for the specific heat of the solution, we do have it, which is this. And the delta T, or the change of temperature, is 5 degrees Celsius. And therefore, we know that the heat release when 0.15 mole of H2O produced is 7,315 joule. There you go. But the question is asking you to find the heat of neutralization. As I told you in the previous slide, heat of neutralization is referring to the production of 1 mole H2O. So we have to find. the heat released by the production of 1 mole H2O, which is equivalent to 48,766 joule. Again, the question is asking you heat of neutralization, so it is good for you to make a new conclusion, which is this. Heat of neutralization is 48.77 kilojoule per mole. Okay, now is it should be negative or positive? Okay, let's see. As you can see here, the temperature rose from 25 degrees Celsius to 30 degrees Celsius, which means heat is released. Therefore, do not forget to add negative here. So negative 48.77 kilojoule per mole. Okay, there you go. Now let's take a look at the third situation. Now the third situation is where the question gives you data, which is the heat release absorbed by both water and calorimeter, or absorbed by both solution and calorimeter. So usually when you get a question like this, okay, you have to apply both both formula, or depends on what data you are given, but usually it will be mc delta t plus c delta t. Okay, so in this case, all heat absorbed by both calorimeter and also either the water or the solution, which is depends on the questions. Okay. So for these questions, okay, we just directly go and see what type of questions related to this situation. Okay, given here, a quantity of 100 ml of 0.5 hydrochloric acid is mixed with 100 ml of 0.5 NaOH in a constant pressure calorimeter that has a heat capacity of 335 joule per Celsius. The initial of the hydrochloric acid and the sodium hydroxide solution is the same, which is 22.5, and the final temperature of the mixed solution is 24.9. Calculate the heat change for the neutralization. And then, given extra data here, assume that the density and specific heats of the solutions are the same for the same for water. Okay, now in this question it gives you, given here, okay, of course this is the quantity like the previous questions, and then you are given the heat capacity of the calorimeter. Okay, the heat capacity of the calorimeter, and then also the change of the temperature, which is from 22.5 to 24.9. Okay, and also it gives you specific heats of solutions. Okay, which means if you have ever seen a question like this where you can see the data for the solution and also the data for calorimeter, then we assume both will absorb the heat release in the reaction. Now let's proceed with the method. Okay, let me illustrate to you guys. It should be something like this. This is the calorimeter, and here is the solution. So it will be absorbed by calorimeter, and it also will be absorbed by the solution. So how are we going to solve these questions? As usual, first thing we have to find the mole for H2O by finding the mole of HCl. So we get 0.05 mole. Don't forget to find the mole of sodium hydroxide. And we are going to get the same thing, 0.05 mole. And as we know, in this reaction, it is always ratio 1 to 1. So everything 1 mole, and this sodium hydroxide also 1 mole, and your water should be produced as 1 mole. But in this case, you are given the same mole for both hydrochloric acid and for both hydrochloric acid and sodium hydroxide, which means the number of mole for H2O produced in this reaction is also the same, which is equivalent to 0.05 mole. Okay, so we know in this reaction 0.05 moles of H2O is produced. Now let's proceed with the next method. Since we know that the number of mole of H2O produced is 0.05, let's find the heat release. Now, as I told you before, because in this question it gives you the data for the heat capacity of the calorimeter and also the specific heat capacity for the solutions, therefore we are going to apply this. Now, we are going to apply MC delta T. This is for solution because you are given specific heat capacity. So, we apply MC delta T plus. Now, since you are given heat capacity, so for calorimeter, we are going to apply this one. Okay, we are going to apply C delta T. Okay. Now, next, we have to find the mass of solution from the volume of the solution. So 100 plus 100, we are going to get 200 ml. So the mass of solution will be 200 gram. Now substitute it in the formula. Substitute also the specific heat capacity and also the delta T, which is 2.4 plus. Now for the calorimeter, we had heat capacity 335 joule per Celsius, and the delta T is also the same, 2.4. So how much heat release we are going to get? Tum tam tum tam, boom. So we get 2 at 10.4 joule. But remember, everyone, this heat release is for the production of 0.05 mole H2O. We were asked to calculate the heat change for the neutralization reaction. So, when we get heat change for neutralization reaction, it is referring to the production of 1 mole of H2O. So, berapa? Tum-tam. We are going to get this one. But again, like I said, we have to rewrite again the answer. It's better. The heat of neutralization is 56.208. Again, I forgot to add the sign negative. Okay, you have to write negative 56.208 because this reaction is producing heat. How do I know it is producing heat? Because the initial and the final, the final temperature is increasing from the initial temperature, which means this reaction is releasing heat. So there you go. This is the answer. Let's take a look at the next question. Now this question is taken from the example 2 from your tutorial book. Let's see. Okay, calculate the amount of heat release in a reaction in an aluminum calorimeter with a mass of 3087 gram and contain 1700 ml of water. The initial temperature of the calorimeter is 25 degrees Celsius and it increased to 27.8 degrees Celsius. Now given to you is the specific heat capacity of aluminium and specific heat capacity of water. Okay, so how are we going to solve a questions like this? this question does not ask you about calculate the enthalpy change or calculate the heat of formation. No, it only says calculate the amount of heat released in a reaction. Okay, in a reaction in an aluminium calorimeter. So maybe you can make your imagination. So this is your aluminium calorimeter, and the mass is 3087 gram, and inside we have water. Okay, we have water. Okay, this is the water, which is 1700 ml, and then that's it. They give you the initial temperature and increase. We also don't know what reaction is happen here, but they give you the mass of the aluminium. Okay, the mass of the aluminium. And the most important thing is that they give you specific heat capacity for both aluminium and water. So this is something different from your previous question. Okay, why I say different? Because in the previous questions, the calorimeter it gives you the heat capacity. But in these questions, for the aluminium calorimeter, it gives you specific heat capacity. Okay, so this is very important for you to identify this, because you have to determine which formula you want to use. Now for this, as I mentioned before, in this question, it doesn't require you to calculate any enthalpy of formation or enthalpy of combustion. The question is just asking you to calculate the amount of heat release in this reaction. Therefore, we have to identify what are the surroundings. So like in this case, as we mentioned before, the surrounding is the calorimeter and also the water. So we apply the formula MC delta T as we are given specific heat capacity for water. And for calorimeter, we also apply the same formula, which is MC delta T. So for water, we are given 1700 ml. So we can find the mass of water by using the density and multiply it with the volumes of water, and the mass of water that we get is 1700 gram. So we substitute this value to the formula given, the specific heat capacity of water, which is 4.18, and the change of temperature, which is 2.8. Now for the aluminium, the mass of the aluminium is 3087 gram, and multiply it with the specific heat capacity of aluminium, which is 0.553, and also multiply it with the change of temperature, which is 2.4. So calculate tum tum, and we're going to get 24,676.71 joule. So that's it, because the question is asking you about heat release in this reaction, not for 1 mole of formation or 1 mole of combustions. Okay, so again, let's rewrite the answer. We write it like this. Looks nice. Okay, heat release in this reaction is 24.68 kilojoule. Okay, sorry for the mistake here, it should be joule, kj per mole. So there you go, this is the answer. So how about if you give a try on some questions. So give a try question 7 and question 8 from tutorial book, and also example from lecture notes. Here's another where of questions. Okay, if you look at this question, it doesn't seem like there's a calorimeter or there's a water in it. However, these questions apply the principles of heat release equivalence to heat absorb. So let's take a look at the questions. Now, a calorimeter contains 400 milliliter of water at 25 degrees Celsius. If 600 milliliter of water at 600 degrees Celsius is added to it, determine the final temperature. Assume that the heat absorbed by calorimeter is negligible. Now, the key, the things that we need to focus on is the statement here, which is heat absorbed by calorimeter is negligible. So means there is no heat absorption by calorimeter. Okay, so let's take a look on how to answer this kind of questions. Now you have to imagine that this is a calorimeter. I'm taking the example of the simple calorimeter, which contain 400 milliliters of water, and we have another water, okay, which is having the volume as 600 milliliter with the temperature 60 degrees Celsius. So what will happen? The water from the cup B, okay, will be combined, and they will be in one in one cup, okay. Both water are mixed together. So we know that water from cup A is 25 degrees Celsius, whereas water from cup B is 60 degrees Celsius. So when we mix these two waters, of course they are going to get into a new temperature, and the temperature should be something like this, which is it should be higher than 25 degrees Celsius, but it should be lower than 60 degrees Celsius. So I named this temperature as TF. So this is what we have to find. We have to find the TF. So how are we going to find it? So we assume that water in cup A will absorb the heat, because of course by right it initially it's 25 degrees Celsius. So after mixing with water from cup B, okay, the temperature will increase, which means the water in cup A is absorbing heat. Now water from water A will absorb heat from water B. So B will release some heat. Okay, B will release some heat to A. And of course, once B is mixed with A, okay, of course the 60 degrees Celsius will decrease. So we apply the MC delta T, which is like this. Okay, so TF, okay, TF for A should be something higher, so we put it in front here. But for B, okay, since the TF should be lower than 60 degrees Celsius, then we put it here. Alright, so let's calculate like this. Okay, now get sometimes, okay, you can pause for a while, calculate and get the TF. Okay, then TF will be equivalent to 46 degrees Celsius. Okay, so this is another applications of the basic principle heat release that is equivalent to the heat absorb. Right? So as you learn the previous questions, try to do the question 10 from your tutorial book. And that's it for calorimeter. Thank you everyone.